Hi, I'm Yang Liu, and I'm going to be starting as an assistant professor in the computer science department in spring of 2025. I wanted to tell you about my research, which is on the modern design of efficient algorithms. In modern times, data is often huge. There's billions of people, billions of connections between them, and this necessitates the need for even more efficient algorithms to process this data. Examples include graphs, which model possibly roads in a network or connections between different people. Another example includes studying optimization problems. We have some data and we want to find the best model line to fit this data as possible. And my research has studied both of these through the lens of something called high dimensional geometry, kind of thinking of both of these objects, which seem very different at first, but viewing them through a common lens as some objects in a high dimensional space. So I just wanted to give some examples of this and what I've done. On the side of graphs, a classical problem is the bipartite matching problem. You can think of this as there's two groups and there's some connections between the groups. Now you want to find efficiently the maximum number of pairs of groups such that no pairs share any member. For example, given these connections, this would be a maximum bipartite matching. To view this problem in a geometric lens, first you can think of a matching as being a vector on the edges. So this is just assigning a 1 to edges that are matched, so the orange edges here, and a 0 to the rest. So this gives us a vector, and thus matchings as some convex set in high dimensions. This gives us the ability to apply convex optimization tools to solve this problem more efficiently. And for example, in my work, I gave a nearly optimal algorithm for bipartite matching and extensions of it. Another example of my work is on the problem of linear regression. Here you have a lot of different data points, and you want to find a best fit line through these points that is best fit in some metric. Initially, there may be a lot of data points, for example, here. So it might be very expensive to find a best fit line. One idea is to reduce the number of points while still hopefully preserving the best fit line. So here, we only are taking a small number of the points, but the fit line through them is approximately the same as in the original set. Thus, after reducing the number of points, we can design more efficient algorithms to solve the problem. This idea is called sparsification. Can you reduce the number of points while still preserving the property of the points that I want that lets us compute a best fit line approximately? And in my work, I've studied in various settings. In what settings is it possible to apply this sparsification procedure? In what sort of best fit scenarios can we reduce the number of points while still preserving the properties we want? I hope that gave just a taste of what my research is on. And if you want any more information, I've linked my homepage here, and I'm excited to join CMU soon. Thanks.